This episode is brought to you by Brilliant. On the morning of June 30th, 1908, a massive explosion in the skies above the Tunguska region of Siberia flattened nearly 2,150 square kilometers, or about 830 square miles of force. Witnesses described a bright flash and a powerful shockwave that knocked people off their feet up to 600 kilometers or 370 miles away. Those closer to the explosion even reported that the flash was brighter than the sun and produced a deep rumble that lasted for several minutes. This explosion was so powerful that it registered on seismographs as far away as England. Known as the Tunguska event, it was believed to be caused by the airburst of an asteroid or comet about 50 to 60 meters or 160 to 200 feet in size at an altitude of 5 to 10 kilometers or about 3 to 6 miles. It was estimated that the asteroid had a kinetic energy of around 15 megatons, or the equivalent to that of an explosion of 1,000 Hiroshima-type atomic bombs. Despite the event downing an estimated 80 million trees and destroying enough forests to cover half of Rhode Island, all while causing hundreds of injuries and even a few deaths, it was not classified as an impact event, as the object never struck the Earth's surface. The Tunguska event is the largest natural explosion on Earth in recorded history. Its effects on the landscape were so destructive that even 100 years later, the area of the blast is still one of the most sparsely populated areas of Siberia. It's even been estimated that the explosion had caused a deceleration of the Earth's rotation relative to the rest of the solar system by 4 microseconds. A little over a century later, another major atmospheric explosion would occur over the Chelyabinsk Oblast at around 27 kilometers or 18.5 miles above the ground. This explosion, caused by a near-Earth asteroid about 20 meters or 66 feet in size, was estimated to have released the energy equivalent of around 500 kilotons of TNT, and was the largest explosion of an object in the atmosphere since the Tunguska event. The Chelyabinsk event caused widespread damage to the city below, with over 7,000 buildings damaged and 4,000 people injured. It is estimated that the total damage caused by the event was around 33 billion rubles, or about $1 billion US. The Chelyabinsk event is a reminder of the destructive power of even small asteroids, and highlights both the frequency of these events as well as the importance of the need to identify and track these potential threats. Both Tunguska and Chelyabinsk represent the ultimate ominous result of a category of astronomical objects known as potentially hazardous objects, or PHOs. PHOs are defined as near-Earth objects, such as an asteroid or a comet, that has an orbit which approaches the Earth at a distance of 0.05 astronomical units, or about 19.5 lunar distances or less. These objects must also possess an absolute magnitude of 22 or brighter, inherently making them massive enough to cause significant regional damage as it enters the Earth's atmosphere or impacts its surface. The vast majority of these objects are asteroids, and as of June 2022, 2,270 of them are tracked, of which 150 are estimated to be larger than 1 kilometer in diameter. 85% of these asteroids are known as Apollo asteroids, as they hold an orbit that keeps them within the inner solar system. While most potentially hazardous objects that have well-known orbits are not a threat to the Earth for the next 100 or more years, 20 objects in particular, with a diameter greater than about 140 meters or about 459 feet, do pose a risk within decades. These are placed on a list known as the Century Risk Table, of which the average object impact probability is around 1 in 300. In order to predict asteroid impacts, they must be detected and their orbits determined. This, however, is an incredibly challenging task, as these objects must be detected against the numerous background stars. This is achieved primarily by sky surveys that are designed specifically to discover near-Earth asteroids. Unlike the majority of telescopes that have a narrow field of view and high magnification, survey telescopes have a wide field of view to scan the entire sky within a reasonable amount of time, with enough sensitivity to pick up faint near-Earth objects. These surveys revisit the same area of sky several times in succession, detecting movement by using image differencing techniques. If an object that moves from image to image against the background of stars is detected, it is checked against the catalog of all known objects, and if it is not already known, its precise position and observation time is reported. Asteroid surveys are generally classified as either cataloging surveys or warning surveys. Cataloging surveys use larger telescopes to identify predominantly larger asteroids well before they approach close to the Earth. They scan the sky slowly, on the order of once a month, but produce deeper, more highly resolved data. Warning surveys, by contrast, utilize smaller telescopes to rapidly scan the sky for smaller asteroids that are within several million kilometers from Earth. These surveys are performed anywhere from nightly to weekly, though they lack the sensitivity to detect objects more than a few days away from passing very close to the Earth. These dedicated survey installations first started to appear around the late 1990s and were initially clustered together in a relatively small part of the Northern Hemisphere. Among them, the most successful survey to date has been the Catalina Sky Survey near Tucson, Arizona. Responsible for the discovery of more than half of the asteroids that are currently on the Century Risk Table, the Catalina Sky Survey has discovered more than 22,000 asteroids since it began operations in 1998. The Catalina Sky Survey employs 3 telescopes, a 1.5 meter telescope on the peak of Mount Lemmon, a 68 centimeter telescope near Mount Bigelow, and a 1 meter follow-up telescope also on Mount Lemmon. These telescopes use thermoelectrically cooled 111 megapixel CCD cameras that are cooled to approximately -100 degrees Celsius or about -148 degrees Fahrenheit, though the follow-up camera operates at just 4 megapixels. Another noteworthy survey is the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Initiated in 2015, this robotic astronomical survey and early warning system located in the Hawaiian Islands is optimized for detecting smaller near-Earth objects a few weeks to days before they impact Earth. Further NASA funding has brought these systems to the Southern Hemisphere, with 2 additional telescopes becoming operational in early 2022 in South Africa. At present, several other Southern Hemisphere-based surveys are also under construction. In addition to ground-based surveys, the Wide Field Infrared Survey Explorer, or WISE infrared telescope in Earth's orbit, was tasked with a 4-month extension mission called NEOWISE to search for near-Earth objects using its remaining capabilities. While this initial extension occurred in 2010, NASA had reactivated the mission in 2013 for a new 3-year mission to search for asteroids that could collide with Earth, and by July 2021, NASA would reactivate NEOWISE once again with another PHO detection mission extended until June of 2023. Currently, a replacement space-based infrared telescope survey system called the NEO Surveyor is under development with an expected deployment in 2026. NEO Surveyor will supersede NEOWISE's capabilities, conducting surveys from the Sun-Earth L1 Lagrange point, allowing it to better see objects within Earth's orbit. While the NEO Surveyor was first proposed in 2006, funding attempts were unsuccessful as science missions took priority at the time to NASA. Despite a mandate issued in 2005 by the United States Congress to achieve a 90% search completeness for discovering, cataloging, and categorizing dangerous asteroids larger than 140 meters by 2020, funding was never appropriated for the effort and it remained largely ignored. In response to the inadequacy of this mandate, in January 2016, NASA, now backed with the necessary funding, would officially announce the establishment of the Planetary Defense Coordination Office, or PDCO, with Lindley Johnson being appointed to lead it as its Planetary Defense Officer. NASA would reorganize its near-Earth object observations programs to better integrate into the PDCO, and extending beyond cataloging and tracking potentially hazardous near-Earth objects, the PDCO would work with other government agencies to develop and update action plans for near-Earth object threats. They also provide expertise on the nature and effect of asteroid impacts to the Federal Emergency Management Agency so that adequate emergency response can be prepared in the event of an impact. The PDCO also coordinates its efforts with the space agencies of other nations, as a member of the Multinational International Asteroid Warning Network and the Space Mission Planning Advisory Group. Since its inception, the PDCO has become attached to 3 key flight missions aimed at planetary defense. The first being incorporating the existing NEOWISE program and its extended mission, followed by 2 groundbreaking asteroid-based missions. The first of these, called OSIRIS-REx, or the Origins Spectral Interpretation Resource Identification Security Regolith Explorer, is a NASA asteroid study and sample return mission. OSIRIS-REx's primary goal was to obtain a sample of a near-Earth asteroid known as 101955 Bennu and return the sample to Earth for a detailed analysis. OSIRIS-REx was launched on September 8, 2016 and rendezvoused with Bennu on December 3, 2018. It spent the next several months analyzing the surface. Then on October 20, 2020, it touched down on its surface and successfully collected a sample. Despite complications from a jammed flap caused by larger rocks, NASA estimated it was able to collect between 400 grams and 1 kilogram of material. At present, OSIRIS-REx is expected to return with its sample to Earth on September 24, 2023, and be extended a new mission to study 99942 Apophis as OSIRIS-APEX. While a handful of landing missions have been conducted previous to OSIRIS-REx, the Bennu asteroid, at just 430 meters or about 1,400 feet, was the smallest object ever orbited by a spacecraft, with OSIRIS-REx orbiting at the closest orbit ever achieved. While the mission was predominantly a scientific mission in search of organic material or the molecular precursors to life on the carbon-rich asteroid, Bennu is also an asteroid that could someday make a close pass or even a collision with Earth, though not for several centuries. This further highlights the importance of possessing the capability to intercept such an object for planetary defense to be effective. The second New Flight mission, and arguably the most ambitious planetary defense project to date led by the PDCO, is known as DART, or the Double Asteroid Redirection Test. Unlike previous asteroid-based missions, DART was designed to demonstrate a potential method for protecting Earth from impact. Developed and led for the PDCO by the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland, DART tested a technique to strike an asteroid in order to shift its orbit. The target asteroid, Didymus, is a binary system which is classified as a potentially hazardous object. At around 800 meters, or about half a mile across, Didymus is orbited by a small moon called Dimorphos, that is about 160 meters, or about 530 feet across. The orbit of Didymus ranges from just outside the orbit of Earth to a bit beyond the orbit of Mars, and takes 2.1 years to make each trip around the Sun. The mission was designed to specifically impact Dimorphos with the small car-sized spacecraft at approximately 6 kilometers a second, or about 3.7 miles per second, with the subsequent change in orbit of the asteroid system being primarily confirmed by ground-based telescopes. The DART spacecraft was designed purposely to be an impactor. At 610 kilograms, or 1,340 pounds, it contains no scientific payload and navigates to Didymus primarily by inertial measurement and a star tracker, with 5 digital sun sensors serving as a backup. DART's propulsion is produced by 2 methods, a traditional chemical system and an ion thrust system. The chemical system is a monopropellant hydrazine system that uses 8 thrusters for launch cleanup, trajectory correction maneuvers, and attitude control, while its primary thrust came from the commercial variant of the NASA Evolutionary Xenon Thruster, or NEXT-C ion thruster. Powered by the spacecraft's 22 square meter solar arrays that generate around 3.5 kilowatts, the NEXT engine uses this generated electricity to accelerate a xenon propellant to speeds of up to 40 kilometers a second, or about 25 miles per second. Ion propulsion operates at near 80% propulsive efficiency, producing continuous thrust for long periods of time, offering superior mission flexibility. The primary sensor on DART for optical navigation on approach and autonomous navigation in the terminal phase is a high-resolution visible imager known as the Didymus Reconnaissance and Asteroid Camera for Optical Navigation, or DRACO. Derived from the New Horizons LORRI instrument, and modified with a commercial 5.5 megapixel sensor, this system autonomously determines the impact point within 1 meter, characterizing the pre-impact surface morphology and geology in the process. This decision to use a commercial sensor was done to reduce cost, as there is sufficient sunlight at the asteroid's intercept point of around 1 AU from the Sun. DART also served as a testbed for new technologies, such as the Small Body Maneuvering Autonomous Rendezvous and Targeting Navigation, or SmartNav, a new system comprised of algorithms, software, and firmware running in FPGA-based avionics, the Rollout Solar Array, or ROSA, and the Gimbaled Radial Slot Line Antenna, or RLSA, for high-gain communications with data rates of up to 3 megabits per second. enclosed in a spring-loaded box, was a piggyback satellite known as LisaCube. LisaCube is a miniaturized satellite weighing just 14 kilograms or 31 pounds. Built to carry out observational analysis of the Didymos asteroid binary system after DART's impact, it was the first deep space mission to be developed and autonomously managed by an Italian team. LisaCube contains only two 4-megapixel optical cameras, one for narrow-field sensing and the other for wide-field. These sensors are designed to capture scientific data, revealing the composition of the asteroid, and provide data for its autonomous system by finding and tracking the asteroid throughout the encounter. DART was launched on November 24, 2021 on a dedicated Falcon 9 mission. The mission payload along with Falcon 9's second stage was placed directly on an Earth escape trajectory and into heliocentric orbit when the second stage re-entered for a second escape burn. Despite DART carrying enough xenon fuel for its ion thruster, Falcon 9 did almost all of the work, leaving the spacecraft to perform only a few trajectory correction burns with its chemical thrusters for most of the journey. On July 27, 2022, the Draco camera detected the Didymos system from approximately 32 million kilometers or 20 million miles away and began to refine its trajectory. LisaCube was separated on September 11, 2022 from DART by being ejected at roughly 4 kilometers an hour or about 2.5 miles an hour. 4 hours prior to impact, DART's SmartNav system transitioned to a completely autonomous mode. By 38,000 kilometers or 24,000 miles away from Dimorphos, SmartNav had assessed all objects in view and established its final trajectory. At 24,000 kilometers or about 15,000 miles away, Dimorphos registered on the Draco camera. These captured images were transmitted in real time to Earth using the RLSA communication system. A few minutes before impact, DART performed final trajectory corrections. The final image was transmitted 2 seconds before impact. At 23:13 UTC on September 26, 2022, DART impacted Dimorphos with an energy equivalent of around 3 tons of TNT, reducing Dimorphos' velocity by an estimated 0.4 millimeters per second, reducing its orbital velocity and bringing it closer to Didymos. This ultimately changed the overall orbit of the asteroid system. While the orbital change in this case was very small, over the course of years, the tiny difference of every orbit will accumulate. An asteroid on a hypothetical collision course with Earth would only require a path shift of around 6,500 kilometers to avoid the Earth, a tiny amount relative to the tens of millions of kilometers it would travel orbiting the Sun. LisaCube flew past Dimorphos about 2 minutes and 45 seconds after DART's impact, capturing images of the impact plume's evolution and newly formed impact crater, as well as capturing the opposite hemisphere of Dimorphos. In October 2024, the European Space Agency will launch the Hera mission, with its primary objective being the validation of the kinetic impact method to deviate a near-Earth asteroid in a colliding trajectory with Earth. Hera will fully characterize the composition and physical properties of the binary asteroid system, including the subsurface and internal structures. It will also perform technological demonstrations related to small body interceptions, and the deployment and the communication with miniaturized satellites in interplanetary space. Hera is expected to arrive at the Didymos system in 2026 and will spend more than 2 years observing the two asteroids, further refining the technologies and understanding needed to proactively defend our planet from cataclysmic impact events. Intercepting an asteroid millions of miles away with nothing more than 4 minutes of a rocket's acceleration and some small thruster bursts requires an incredible understanding of ballistics and the motion of celestial bodies. Orbital mechanics is at the core of space exploration, with differential calculus being one of its most fundamental tools, and with Brilliant, building an empowering understanding of calculus has never been easier. Brilliant is my go-to tool for diving headfirst into learning a new concept. It's a website and app built off the principle of active problem solving. Because to truly learn something, it takes more than just watching it. You have to experience it. With this in mind, Brilliant has been tirelessly revamping their courses to introduce even more interactivity. And with their recently updated Calculus in a Nutshell course, you'll be able to explore and examine calculus's wide scope and depth of application from a bird's eye view, using visual and physical intuition to grasp its major pillars. You'll walk away with a clear sense of what calculus is and what it can do. With Brilliant, you learn in depth and at your own pace. It's not about memorizing or regurgitating facts. You simply pick a course you're interested in and get started. If you feel stuck or made a mistake, an explanation is always available to help you through the learning process. If you'd like to try out Brilliant and start learning STEM for free, click the link in the description below or visit brilliant.org/newmind, and the first 200 of you will get 20% off an annual premium subscription.